All right, this is section 4344. There was one example that we skipped over in class, and it was mainly because it was not the type we would test you on, but at the same time, this is a good one to exercise the practice of why the C over D rational root theorem doesn't always work. So if we look at this specific polynomial that's given to us, and we want to go ahead and make our C over D list. So C is, remember, the constant term, and D is the coefficient of the leading or highest power one, so that's your leading coefficient. We want factors of C, and that would be 1 and 7. We want factors of D, which would be 1 and 2. So my C over D list is, remember, all possibilities that are positive or negative of the following: 1 over 1, 7 over 1, 1 over 2, 7 over 2. So there's 8 possibilities here. Now, you can go through and use the remainder theorem and plug those in one at a time and prove that none of them equals 0. That's one way of doing it, using the remainder theorem. You could also do it using synthetic division, making sure you put in 0 placeholders for any missing powers, which there are quite a few. Show that that doesn't ever come out to 0. So there's 2 different methods. Now, we did a lot of synthetic division in class, so I'll show you using the remainder theorem because it'll take up less space to write all of this, because we have 8 different possibilities to try because there's positives and negatives. So if we plug in f of 1, remember when you do an evaluation of a number in a function, the answer we get is what the remainder would be if we had done the division of that. So this is 2 times 1 to the 5th plus 3 times 1 cubed plus 7. So that is 2 plus 3 plus 7. So that is 12, which is not 0. And so therefore that doesn't divide evenly if we made that a factor of x minus 1. If we plug in negative 1, do the same process. This time, though, we have to actually think about it. Negatives that get raised to the odd power are going to stay negative. So this ends up being negative 2. And you can use your calculator for this. This is a negative to the odd power, so it's going to be negative. So that's going to be negative 3 and then plus 7. That's negative 5 plus 7. That is 2. Also not 0. So the remainder is not 0. Then we would do positive 7. Just going through our list. And this might be where you want to especially start using your calculator, because these are going to get pretty large values to them, especially to the 5th power. So 7 to the 5th is 16,807 times 2 is 33,614. Definitely not looking very promising there. And then we have 7 to the 3rd. So 7 to the 3rd, that's 343 times 3. That's 1,029. Just using my calculator for that. And then plus 7. Yeah, I don't even need to add all that together. Not 0. It's all positive. It's just going to get super huge. Then I would apply negative 7 in. So this is plus 7. That's just going to change these first and second terms to negatives because the negative is raised to the odd power. The number values are the same, just negative now. And again, don't really care what that is. I can obviously see that's not 0. Okay, so now we try the fractions. F of 1/2 is 2 times 1/2 to the 5th plus 3 times 1/2 to the 3rd plus 7. This will be 1 over 32 because 2 to the 5th is 32. And then 2 over 32 is 1/16. Again, you can use your calculator for these. 2 to the 3rd is 8, so that's going to be a 3 over an 8, since that doesn't reduce. And then plus 7. Again, I know that those are all positive. That's not going to zero out. So I don't have to check too deeply if I can see a trend that it's not going to make a negative. Cancel out with a positive, and we're never going to get 0 from that. But again, you can plug it all the way into your calculator and get the actual value. What we're just trying to prove is that the C over D list that we've come up with using our rational root theorem cannot find the zeros for every single problem because not all of them have rational zeros. So this one, let's see, that's going to be just negatives of what we got before. So that's -1/16 and -3/8 and +7. Since there's some negatives and some positives, I should probably check this one by getting common denominators. So that's going to be -6/16 +7, and that is going to be -7/16 +7. That does not equal 0. Not 0. Because 7 turned into a common denominator with this would be much larger. And then we would do the same thing with 7/2 and -7/2. Now I'm not going to go through and prove all of those individually, but use your calculator. Okay. But you can kind of see the gist of it. So if you've exhausted our whole list, so we exhausted the C/D list, so cannot solve or factor by using the rational root theorem. So that begs a big question, you know, what kind of solutions would this have? It could have some imaginary conjugate pairs. It could have solutions that have radicals in them. So it's definitely not something very nice that we can solve using our rational root theorem. And in fact, I went to a website that can do some higher level mathematics. So let me share my screen with you. And this is the polynomial that we were trying to solve. And the answers are, if you notice, there's one really kind of nasty decimal, just regular decimal answer. And then there's conjugate pairs that are imaginary. Now this is approximating them with decimals, but you know, this is nothing that the rational root theorem could have helped us to solve. It does not have the ability to solve things that don't have rational roots. So yeah, if we put it in exact form, I don't know if it gives it to us with the radicals. No, it looks like it's just going to give approximations no matter what. But you know, that's why we couldn't solve it using the rational root theorem. But we knew that just by doing the process of elimination. We went through all the possible C's over D's. So we know that the answers are going to be something with radicals that we can't solve. And they're also possibly imaginary conjugate pairs. And that gives us a total of 5 roots. So 2 imaginary conjugate pairs and 1 that just has some kind of nasty square root involved. Okay, and that gets us caught up on this section.